Good morning, everyone. In today's GATE class, we are going to learn about electrical and electronic measurements. So this is a subject which has a weightage of 5 to 6 marks in every competitive exam, including GATE and other type of AP Genco Transco type of exams. So this is a subject which has very little bit of syllabus coverage. In this, the main topics covered under this measurement subject was bridges, potentiometers, measurement of voltage, current, power, and energy, which is the basic parameters to be measured using some instruments. And here, while coming to the other type of extinction meters, we are going to learn about instrument transformers, digital voltmeters, millimeters, and phase, time, and energy meters. And coming to other type of electronic measuring instruments, we are going to learn about oscilloscopes. That's nothing but cathedral oscilloscopes. This subject is which comes under electrical engineering. It comprises of weight of 5 to 6 marks. And generally, based on the previous papers analyses, we can come to that the major topic covered under the syllabus was bridges and potentiometers and measurement of voltage, current, power, energy, and power factor. And there are some papers which has been covered with error analysis and digital voltmeters and multimeters. So the referred textbook for this was A.K. Shane. So the basic textbook to be followed, and which has more number of examples, either in terms of theory or in terms of problematic subject problems. Examples, numerous examples has been solved under this textbook. And coming to the previous papers analysis, so based on the GATE question paper, these are the major topics which has been covered under every year. While coming to the recent paper of 2021, they have been asked 3 questions under a frequency measurement and digital voltmeter, error analysis, and output of a instrument transformer, which is nothing but a current transformer. Whereas coming to 2020, they have been asked on error analysis and reading in ammeter. And coming to 2019, it was extinction of range of voltmeter, which is nothing but extended value, how we are going to measure the value of voltage and current transformer. And coming to the 2018 and 2017 and 16, so these are the various terms that has been regularly covered. So based on the scenario of the coverage of the questions in this subject, in today's class, we are going to discuss about bridges and um, potentiometers. So coming to the bridges, so let me open the Jamboard. So coming to today's topic, so in this electrical measurements, so the subject what we are going to learn here in today's class was electrical under the stream of electrical engineering. So the subject name was, it was electrical and electronic measurements. For this subject, so it is going to carry a 5 to 6 marks of weightage. So the basic term that what you have to refer here was, the first and foremost things that you have to concentrate was error analysis, and bridges, and then oscilloscopes for electronic measurements. So these are the major topics which has been continuously asked, and these were the questions which has been covered under these topics. And there are some papers where it has been referred with potentiometers, nothing but extinction of measurement of voltage range. So here, coming to the class today. So in today's class, we are going to learn about bridges, various types of bridges. So in this bridges, we have 2 types, AC bridges and DC bridges. Coming to AC bridges and DC bridges, so bridges are just like, so in this class today we are going to learn about bridges. So these bridges are used as devices or instruments which are going to measure resistance, inductance and capacitance. So these are the basic elements. We know that if you want to measure voltage, current or power, so for voltage we have instruments like voltmeter, whereas for current we have ammeter, whereas for power we have wattmeters. So in the same way, if you want to measure the elements which are carrying or elements which are running with these voltage, current, and power, so these are the elements which have been used as a basic elements for a circuit. So the elements which are considered as active elements and passive elements in that perception. So these elements will be called as the passive elements, where the R refers to resistance, L refers to inductance and C refers to capacitance. If you want to measure the elements of resistance, inductance and capacitance, we have to rely on the values like bridges. So there are two types of bridges. So based on the supply, we can bifurcate them as DC bridges. And here one more classification is AC bridges. So DC bridges are nothing but which consist of, it is a bridge which consists of four limbs with only resistors on either side, and it is connected with a DC source. And in between we will have a balancing circuit called galvanometer. So whereas coming to AC bridge, so it is also comprised of same four limbs. So and this comprises of AC source. So here also it will consist of galvanometer. And if you coming to DC bridge, so DC bridge is where it is used for measurement of resistance only. And here the source will be a battery and it consists of a DC galvanometer. And here the balanced equation will be the two limbs, adjacent limbs should be equal to each other. So PS is, if you consider this as P and Q, S and R. So these limbs P into S is equal to Q into R. So this is a balanced condition here and this is used only for the measurement of resistance. Whereas coming to AC bridges, so AC bridges consist of AC source or oscillator, AC source or oscillator, and here the galvanometer used was a vibrational galvanometer, which is and here the balanced condition will be, as here in DC bridges we have considered as it as resistances P, Q, R, S, whereas coming to AC bridges here the limbs will be considered as impedances Z1, Z2, Z3 and Z4. So these are the limbs and here the balanced condition will be Z1, Z4 is equal to Z2 into Z3. As it is AC1, here the phase angles will be considered. So theta 1 plus theta 4 is equal to theta 2 plus theta 3. So these two are the balanced conditions for AC bridges. And these AC bridges are exclusively used to measure inductance, capacitance, Q factor, dissipation factor, and also frequency. So the AC bridges are the bridges which are used to measure inductance, capacitance, quality factor, dissipation factor, and frequency. So here always remember DC bridges are meant to measure only resistances, whereas AC bridges are meant to measure inductance, capacitance, wave factor, D factor, and frequency. So coming to the next task, so how many, as if we know that these are the bridges which are going to be used here. AC bridges, coming to the DC bridges. So as we got a conclusion that these bridges are meant to measure resistance. So here the resistance is classified into three types. One is medium resistance, low resistance and high resistance. So here the resistance will be measured by using various methods in terms of the range. So low resistance, medium resistance and high resistance. If the value is less than 1 ohm, if the value of measurement of resistance is less than 1 ohm, then the resistance will be considered as low resistance. If the value is in between 1 ohm to 100 kilo ohms, then it will be considered as medium resistance. If it is high resistance, it is more than 100 kilo ohms. So this is how the classification of the resistance is done. So whereas coming to application point of view, this 1 ohm of resistance is always observed in the place of internal resistances in all the motors and generators, transformer windings, earthing conditions. Whereas value 1 ohm to 100 kilo ohm is observed for DC shunt fielding windings, whereas heater coils, human body resistances, whereas voltmeter resistance like that. Whereas coming to high resistance, it is used for cable insulations. So cable insulations of all the motors, generators, transformers, and semiconductor also. And coming to the classification, after knowing the classification, so here we can use methodologies to measure low resistance was. So to measure low resistance value, we have a method called Kelvin's double bridge. Kelvin's double bridge method, or we can go for potentiometer method. Whereas coming to measure medium resistance, for medium resistance we have volt ammeter method or substitution method or Wheatstone's bridge method and ohm meter method. So these are the various methods which is used to measure a range of 1 ohm to 100 kilo ohms. Whereas coming to other high resistance methodology, so coming to high resistance, we have loss of charge method, Megger method, mega ohm meter method, and direct deflection method. So these are the various methodologies which are used to measure resistance. As we are going to learn about bridges here, so we are going to see about Kelvin's double bridge and here Wheatstone's bridge. So high resistance, we don't have, we won't use any sort of bridges. So here, as in the perception of bridges, here we are going to learn about Kelvin's double bridge and Wheatstone's double bridge. So here you have to remember one point, that is Wheatstone's bridge is a basic version of measurement of resistance. Based on this Wheatstone's construction, a small internal resistances will be double circuit of Wheatstones will be considered as Kelvin's double bridge. So that's why it is named as double bridge. So it is a modified version of Wheatstone's bridge. Kelvin's double bridge is a low resistive bridge, measurement of low resistance it is used for. But this bridge is a remodified version of Wheatstone's bridge. So we'll first see about Kelvin's double bridge, how the construction will be. So here, Kelvin's double bridge is used for measurement of low resistance. So Kelvin's bridge. So Kelvin's bridge will be seen as the balanced condition for this Kelvin's double bridge is, we have to remember the simple thing here. We are going to calculate the internal resistance, and if you observe the bridge, this will be the construction. So consider a bridge like this. So as it is a resistance one. So here will be a galvanometer. And from this point, so adjacently there will be one more resistance. So here one more resistance, and this is our internal resistance small r, and this is our bridge. So and these terminals are completely connected to a DC source, and this is connected in this. So this is the major bridge P, Q, R, S. Whereas if you observe there is a double bridge, right? So based on the double bridge condition, this will be considered as a small bridge PQ. All the terms is represented with small letters, and here it will be seen the terminal. This will be considered as internal resistance R. So here the value based on this bridge balance condition. So we are going to calculate the values here. So always remember that the bridge balanced condition will be P by Q is equal to small p by q. So this is the condition that what you have to remember. And based on this condition, we are going to calculate the value for low resistance or internal arm resistance. So P, Q are considered as internal arms, whereas S reference standard variable resistance, and this R refers to leads resistance or terminals contact, and these are as unknown resistance. So we know that balanced equation will be, this is the equation for Kelvin's double bridge. It is used to eliminate. Generally, Kelvin's double bridge is used to, advantage of Kelvin's double bridge is used to eliminate, it is used to eliminate the lead resistance effect, to adjust to micro ohms range. So micro ohms, milli micro, so less than 1 ohm, right? So here we are going to adjust the value of low resistance to micro ohms range. So this is the main advantage of Kelvin's double bridge. And whereas the difficulty among measurement of low resistance is the terminal resistances or winding is used to reduce the inductance effect. So the thermoelectric EMF will be very minute. The value cannot be measured properly. So here, but while coming to the advantage, it is used in many advantages. And coming to the medium resistance, the next method. So to measure medium resistance, so we have a bridge called Wheatstone's bridge. So this is the basic bridge that what you have to learn. So before learning Kelvin's double bridge, it is much basic thing that you have to know about Wheatstone's bridge. So Wheatstone's bridge is a basic bridge. Based on this Wheatstone's only, we are going to define our Kelvin's double bridge. So while coming to this bridge, so this is how the connection will be. This is a bridge which you have learnt in your lower classes also. So this is our basic bridge, and here we will observe a galvanometer, deflection galvanometer, and this is where the DC supply is connected, and the representative terms will be Q. So it depends on the conditions that what you are going to take the variables. So here this is a method which is used to measure resistance, which is nothing but a medium resistance value. So here the balance condition will be PS is equal to QR. So based on the adjacent bridges product will be equal to either on the sides. So while coming to the accuracy, Wheatstone's bridge is more accurate bridge. And here you should know a term called sensitivity. Sensitivity is nothing but deflection and current passed through the galvanometer. If it is of voltage sensitivity, then SV is equal to deflection of the galvanometer into the voltage seen across the galvanometer terminals. And one more term you can see is bridge sensitivity. Bridge sensitivity is nothing but it is a ratio of internal resistances. So these are the basic parameters that what you have to know regarding the calculation of bridges. So in case of bridge circuits, sensitivity is very important factor which is used to identify the accuracy, precision, etc. So here we have to remember these points under the Wheatstone's bridge. Whereas coming to measurement of high resistance, so the term high resistance measurement, we have various methods to follow up on. So here first method is loss of charge method. So loss of charge method is a method which is used to find the cable insulation value, and here the value of the resistive value is observed in terms of cable insulation resistance 0.4343 T by C log 10 V by Vc. So here these represents the values of testing resistance value, unknown resistance, in terms of discharge through the resistance. Here, the loss of charge method represents the value of discharge. It depends on the how much the discharged value is calculated through resistance. So this is how the value is calculated. Whereas coming to direct deflection method, so direct deflection method is nothing but it is used as a guardware system where it is calculated through error value. Whereas coming to Megger method it consists of two coils, potential coil and current coil. Based on the deviation existing between these coils, it is used to measure the high resistance values. Megger, generally the Megger is used for measurements of values rating above 500 volts or 1000 volts or 2 kV or 2.5 kV like this. So minimum application of Megger will be less than 100, sorry, more than 100. So this is used to measure the winding insulation resistance of motors, generators and transformers. Here the point you have to remember is in series meet in Megger the spring control is not used. So there is a question which has been asked regarding this Megger. The controlling torque in a Megger is provided by. So it is nothing but there is no control torque here. So it doesn't need any controlling torque. That is the answer. So like this, there are numerous questions which has been asked on DC bridges. But while coming to AC bridges, so AC bridges are so AC bridges, the main concept, the AC bridges are used to measure inductance, capacitance, frequency, and quality factor and dissipation factor. So these are the other two factors that what we learn. So coming to the AC bridges consist of impedances as limbs. Instead of resistances, here we are going to observe unknown inductance or unknown capacitance, Q factor, loss angle. In all the bridges, unknown impedance is measured in terms of impedances. So here the bridge is always balanced by varying values of R or C. So either in terms of resistance or in terms of capacitance. So here, if you observe the bridge, AC bridge, so as here it is comprises of impedances, the bridge construction will be observed like this. So these are the four terminals here where we are going to observe with impedances Z1, Z2, Z3 and Z4. So this is Z2. So and this is completely connected to a AC circuit. Here the balance condition will be Z1, Z4 is equal to Z2, Z3 and angle condition will be theta 1 plus theta 4 is equal to theta 2 plus theta 3. So this is the balanced condition for AC bridges. So here the galvanometer is used as a vibration galvanometer. AC galvanometer is used to find out the balance of AC bridge. If the bridge is balanced, then the condition will be measured with. So this is our galvanometer, which is called as vibrational galvanometer. So sometimes we may use here headphones also if the frequency. This system consists of two speakers in parallel. If the bridge is balanced, the voltage applied for the frequency will be zero. So sound energy will be zero. So like this, we may use either deflection galvanometer or bridge headphones also. There are some parameters where this galvanometer can be replaced with tuned amplifier. So electronic. So finally, you have to remember the balanced condition of bridges. So here first we'll learn about inductance, measurement of inductance. So AC bridges are meant to measure inductance and capacitance. Here The first type of AC bridges that we are going to use for measurement of inductance are five types. There are five different bridges which are used for measurement of inductance. First bridge is Maxwell's bridge, Maxwell's inductance bridge. And the second bridge is Maxwell's inductance and capacitance bridge. Next one is Hayes bridge. And next one is Owens bridge. And fifth one is Anderson's bridge. So these are the five types of bridges which are used to measurement of inductance. Here the most accurate bridge was Anderson's bridge. So this is our first bridge, general circuit bridge diagram here. So at a balanced condition, what will be the magnitudes and what will be the angle condition? So this is our bridge which is used here. So this is our balanced bridge Z1, Z3, Z2 and Z4. The balanced condition will be bridges for Ixinas like this. So these are the various bridges that what we are going to learn for measurement of self-inductance. So first one is Maxwell's inductance bridge. So this is a basic diagram that what we can observe for Maxwell's inductance bridge. So here it comprises of impedances in a combination of resistance and inductance here R1 and L1, whereas here it is R3, this is R4 and this is R2 plus L2. So here the unknown inductance will be considered. So here L1 is considered as unknown inductance based on the balanced condition. So here the unknown values are calculated like this. So R1 is equal to R2 R3 by R4 and L1 is equal to L2 R3 by R4. So here you have to remember how I'll let you know the things. So I'll make you sure that how to calculate for one bridge. Then you can implicate all those things to other bridges also. So if you have considered the first bridge as Maxwell's inductance bridge, Maxwell's inductance bridge. So here the bridge is comprised of four limbs. So as it is a impedance, here the impedance is a combination of resistance and inductance. And on another bridge, another limb, it is also a combination of resistance inductance. And coming to the fourth, so here it comprises of only a resistance. And even on the third limb also it is a only resistance. So this is R3, this is R1, L1 and these two resistances are variable in nature, R2 and L2. This is our R4. So and here we are going to connect a deflection galvanometer which is a vibrational one and this is connected to AC supply. So this is a basic circuit diagram of an inductance bridge. So by seeing this condition, so we can write that R1 plus J omega L1 into under balanced condition. So we know that adjacent will be same, right? So this is Z1 into R4 is equal to Z2 into R3. Z1 into R4 is equal to Z3 into Z2. So based on this condition, I am writing here. So R2 j omega L2 into R2. So based on these equations under balanced condition, we can come to a conclusion that R1 into R4 is equal to R3 R2, where R1 unknown resistance is R1 and L1 is unknown here. So based on this, R1 is equal to R2 R3 into R4. So whereas coming to inductance, L1 R4 is equal to R2 R3 based on the balanced conditions. So here L1 is equal to L2 R3 R1. So here this is the unknown inductance which is going to be measured with help of Maxwell's inductance bridge. So to make this bridge balance, the condition that what you have to remember is R2 and L2 should be balanced. So select uncommon elements from the above two equations. So here we have to calculate if it is of Maxwell's inductance bridge, then a slight modification will be observed in this equation. So here for the R4 we are going to connect a capacitance. So here the value of capacitance is known. So based on this equation, we are going to calculate Maxwell's inductance and capacitance. If it is named as exclusively inductance bridge, then don't keep a capacitor here. So then this will be the equation. If the bridge is named as Maxwell's inductance and capacitance bridge, if it is Maxwell's, the second type of bridge that what we have seen is Maxwell's inductance and capacitance bridge, then the same circuit will be modified like this. Inductance and a resistance and variable resistance and an inductance, and here a resistance. So this is our Maxwell's inductance bridge. But if it is named as Maxwell's inductance and capacitance bridge, then we observe a capacitance which is placed in the R4 limb. So this is a variable capacitor. So using this bridge, we can also calculate the value of capacitance when the inductance is known. So here this Maxwell's inductance capacitance bridge can be calculated in either way. That is, if the capacitance is known, then we can identify the value of inductance. If you don't know the value of inductance, so then you have to relay the value of capacitance. So here the balance condition will be observed as R1 R4 is equal to R2 R3. R1 is equal to R2 R4 by R2 R3 by R4, whereas unknown resistance L1 is equal to R2 R3 R4. So while coming to the calculation of inductances, you should know a term called quality factor. As name itself indicating, it is going to define the quality of the bridges. So this quality factor is a major factor which is going to identify the effectiveness of the bridge what we have designed. So quality factor is a term which is to be identified to which is to be calculated, which is to meant to identify the um, how much effective the value has been attained. So in earlier DC bridges, we have learnt about sensitivity of the bridges in terms, whereas coming to AC bridges for the measurement of inductance, so you should know the term called quality factor. So based on the value of quality factor, so if you come to the major classification, so this is a basic bridge, whereas coming to the quality of the bridge, so this is a bridge which is used when the quality factor value is medium. If Maxwell's inductance and capacitance bridge is used only for medium quality factor values, that is lying from 1 to 10. Whereas Hayes bridge is used for high quality factor values, high quality factor where the value is more than 10. Whereas Owen's bridge is used for incremental conductance or inductance method, whereas Anderson's bridge is used for only for low quality coils, that is nothing but Q is less than 1. So based on the quality factor, the selection of the bridges are going to lie. So here So the quality factor plays a major role in terms of inductance measurement, whereas in terms of other bridges, so next other bridges are Hayes Bridge. So the Hayes Bridge condition is in Hayes Bridge also a capacitor will be seen in the R4 limb. So here the balanced condition and unknown factor will be like this. Unknown inductance. The formulas are the major things to calculate a problem here. So you have to practice these balancing equations. So here the balanced equation based on the Hayes Bridge balance equation. So the unknown values will be considered like this. By 1 plus omega square r4 square c4 square. So this is how the value will be, and the quality factor will be omega L1 by R1, which is equal to omega R4 C4, either in terms of inductance or in terms of capacitance. So this is the slowest bridge when compared to all other bridges, whereas Anderson's bridge is the most accurate, right? So whereas coming to Hayes bridge, it is the slowest bridge of all the bridges for the measurement of inductance. Coming to the next one, next bridge is Owen's bridge. So in this Owen's bridge, the balanced condition will be same for all the bridges. So and the unknown value L1 is seen as R2, R3, C4, and unknown resistance as C4 by C2 into R3, and the quality factor is omega L1 by R1 or omega R2 C2. So this bridge is much suited for medium quality factor. So please remember such type of points. There may be some 1 mark bits based on this quality factor also. So here this is a method which is used for medium Q factor. Women's bridge is also used for incremental conductance also. Incremental inductance method mu naught. So whereas coming to next bridge is Anderson's bridge. So Anderson's bridge is very important, which is the most accurate bridge of all for measurement of inductance. So it is a 5-point bridge. So if you observe the notes, so in every bridge there will be 4 points, but here it will be seen as 5-point bridge. So at the place of galvanometer, there will be one more capacitor connected. So this is a 5-point bridge. So this is how the bridge construction will be. R1, L1, small r1, A, B, C, D, and this is the 5th point E. So here this is R2, and this is variable resistance small r, and this is R3, and this is R4, and this is our capacity. So this is how Anderson's bridge is constructed. So here the Anderson's bridge has a fixed capacitance. So here it consists of a fixed capacitance C, and for the bridge balances, the resistances for bridge balance condition in Anderson's, small r1 and small r are considered as variable resistances. So this Anderson's bridge is generally used for low quality factored bridges, and here the range of inductance measurement will be from milliohms. So the range will be less than millihenries. So here this is a modification of Maxwell's inductance bridge. So here the unknown values will be considered as L is equal to R3, R4. If you observe, there is no other inductances apart from this. So this unknown inductance is measured like this. So this is the formula. and the unknown resistance R1 is calculated like this. R2, R3 by R4 into R. So in any sort of bridge, the condition that what you have to remember is how to balance the bridge. So the main disadvantages of this Anderson's bridge is it is complex in strategy and the shielding of bridge is also much complicated. So in next we are going to learn about measurement of capacitance. So up to now we have seen various bridges. So to measure capacitance, so we have various bridges like Dissortis bridge. So for first bridge is Dissortis bridge, and next one is shearing bridge. So these are the two bridges that what we are going to use under measurement of capacitance. And one more bridge is also there, that is modified Dissortis bridge. So these are the three bridges that what we are going to learn for the measurement of capacitance. So to if in inductance we have seen a term called quality factor, whereas coming to capacitance we are going to see a factor called dissipation factor. So how much energy has been dissipated